Welcome back, guys, to this channel. So, a lot of you have been recently been quite understanding of my teaching. So, basically, today I'm going to be considering Laplace transform. So, basically, my previous video was talking about fluid mechanics and so on and so forth. So, I'm going to be considering Laplace transform. Laplace transform is another topic on engineering mathematics. So, basically, advanced engineering mathematics. So, I want you guys to follow me step by step and you understand what I'm trying to say. So, we're going to be considering Laplace. So, like I said, we're treating Laplace transform. Laplace transform is basically a topic on engineering mathematics. So I want you to follow me step by step, and you really understand what I'm trying to say. So, now, what is Laplace? Laplace is basically a method in which we can easily, it's just basically a method of solving basically equations given. It can be differential equations, it can be algebraic equations. So any kind of equation given, Laplace is basically a method of easily getting your answer. Now basically it also deals with variables x and y, but basically Laplace basically deals with x, basically x and t. So I'm going to consider basically the function t. That is the variable we're going to make use of in Laplace. Now for example, take for example the general form of second order differential equation, which can be written as now, basically, the class is basically dealing with this function of t in the general expression given. So Laplace is basically considering a function. It's simply an ordinary function, a simple function of a variable. Now, it can be trigonometric function, can be algebraic function. So basically, we are simply considering this function of t. So Laplace is represented by the symbol L. Laplace is represented by the symbol L. So Laplace of any function we are given, there is a general method of solving that function to get your answer. So Laplace is basically a method of solving differential equation. So Laplace of this function of t, there's a general expression. So Laplace of any function, or Laplace of any function of t given, Laplace of function of t is equal to the integral starting from 0 to infinity of the function of t exponential minus st dt. Now, I believe this is what you need to jot down if you are following me. So Laplace basically of any function of t is basically the integral starting from 0 to infinity of the function of t exponential minus st dt. So I believe you need to jot down this expression. So Laplace of a function of t, I'm going to take it again, is the integral starting from 0 to infinity of a function of t exponential minus st dt. So now I'm going to explain what this is all about. Now basically, as time goes on, we will not need to be making use of this, but when we have derived our standard expression, our standard solutions to some Laplace expression, we don't need to write out this. So now I'm going to explain what this is. Now Laplace, this is the integral. We're going to be integrating the function of t with the exponential of minus st dt with that with respect to t. So this is the integral starting from 0 to infinity times the function of t exponential minus st dt. So now Laplace is basically regarded as a semi-infinite integral. Why is it called a semi-infinite integral? Basically because it starts from 0 to infinity. Now normally we have numbers coming from negative infinity to positive infinity. So 0 is at the middle of every number coming from negative infinity to positive infinity. So basically we are not considering numbers coming from negative infinity to positive infinity. We are considering numbers just starting from 0 to positive infinity. What I'm trying to say is that we can have number coming from negative infinity. The negative numbers coming down, on the number line we have negative numbers coming down to 0 then to positive numbers. So negative infinity then down to 0 then to positive infinity. So basically Laplace deals with numbers coming from only 0 to positive infinity. So in our limit, you're not going to be seeing any negative value, just positive values. So we're going to consider not only positive values starting from 0 to negative infinity. So this is the function of t. Given you have to find the Laplace of, then this expression minus st. This s is basically what helps for the convergence of the figure at any point in infinity. So now we're going to be going straight to examples so you understand what I'm trying to say. Now after we've derived a few expressions, or basically I might not need to derive all of them. I'm going to just derive some and give you some examples for you to take on it. So now Laplace, example 1. So for example, we're given the Laplace of a. Now I want you to follow me step by step. So for example, we are given the Laplace of a. So Laplace of a, now we're going to rewrite it as this. So writing it as this, we have Laplace of a, which is given as the integral starting from 0 to infinity. Now in this case, it's not function of t. Now it's a. So this is a times exponential minus st dt, right? So now, for example, this is the Laplace of a. For example, you have to find the Laplace of a. So basically, we switch over to this other side. We are going to solve this expression. So before we integrate this, before we apply the limit, which is 0 to negative infinity, we have to integrate it. So since a is regarded as a constant, so taking a to the back of the integral, I want you to follow me step by step. As time goes on, we'll not need to be doing this integration. So this is basically for you to understand how some general expressions are derived, or how some standard Laplace solutions are derived. So taking a to the back of the integral sign, so this is a integral starting from going from 0 to negative infinity, right? Then we have a exponential minus st dt, right? Now, a is taking it back to the integral sign, so this is exponential minus st dt. So basically, we are going to be integrating exponential of minus st dt before we apply our limit. So this is a integral 0 to infinity. Integrating it first, we have exponential minus st dt. So we're going to be integrating this. So integrating exponential minus st with respect to t, right? So integrating an exponential, remember we're integrating it with respect to t. So this is going to be given as a exponential minus st divided by minus s, right? Then taking our limit from 0 to infinity, right? So this is a exponential of minus st dt. We've successfully integrated from 0 to infinity. We're going to be applying our limit. So applying our limit in infinity. Now remember, this is a limit. It's not basically like our normal. So we're going to be applying my definite integral. So starting from 0 to infinity, right? So we're going to be applying the limits given. So we having, remember there's a figure here, a. So we having a limiting when t, limiting t to infinity, right? So we have t to infinity of exponential minus st divided by minus s minus limiting t to 0 of exponential minus st divided by minus s, right? We are going to be applying the limit to infinity and t to 0. So t to infinity, exponential of infinity is always 0. In fact, the exponential of infinity is what? 0. So we have a open bracket t to infinity, so exponential of infinity is 0, right? So this is 0 divided by minus s minus limit t to 0, so this is exponential of 0, right? So this is exponential of 0 divided by minus s. So 0 divided by minus s is basically 0, right? So we having a open bracket 0 minus minus is plus, right? So this is plus exponential 0 divided by s. So exponential of 0 is what? 1, right? So we're having a open bracket 0 plus 1, that's 1 over s, right? Equals to, so the Laplace of a is equal to a divided by s. So I want you to take note of this. I want you to jot down this. So this is basically another standard solution to Laplace. So Laplace of a is a constant. So Laplace of any constant, it can be 3 or 4 or any figure, is basically 4 over s. So I want you to take it an a standard example. I want you to jot down this. This is our first standard solution to Laplace. So this is Laplace of a constant. So Laplace of 4 is basically what? 4 over x. So let's take an example. So example 2. Laplace of 4. What is Laplace of 4? Another example. What is Laplace of 5? So I'm going to do the first example and you do the second example. So Laplace of 4. What is Laplace of 4? Now, given our standard expression, our standard solution here, Laplace of a, which is a constant, is basically what? A over s. So given Laplace of a, which is a over s, Laplace of 4 is basically what? 4 over s. Bravo. So I'm going to leave you to the second example, and that's that. So this is basically our first stage of Laplace of a constant. So I want us to go over to the second stage, which will proceed to further solutions to standard Laplace expression. So I hope you understand this aspect. So see you in the next one.